let's look at a summary of the FEM procedure. Okay, what are the various steps that we have to do? Okay, so what do you think would be step number 1? Okay, so for definiteness, let's assume a problem. Okay, this is my aircraft over here. And I want to calculate RCS, the radar cross section of this aircraft. Okay, you are given some incident radar field over here. Okay. What is step 1? You are given this problem. Let's say you are a aircraft designer or a ship designer. You are given this problem. What would be step 1? How do I start solving this problem? Huh? Well, before that, even before that, think really basic. Break it into triangles, right? Now, how do I break it into triangles? What is the tool that I need for that? Right? So, I need to generate a mesh file, right? So, that is CAD software. Okay, AutoCAD is a popular one. In open source, there is what Gmesh is one popular software. So, there are many ways of doing it, right? So, generate a mesh file, store it. So, for complicated objects, this is itself a big task. Imagine you are given, let's say, like some MiG-21 or something. You need to have a realistic 3D model of this in the computer, and then you have to further fracture it. Okay, a real life object will have some very tiny things here and there which need not be meshed. So, you should smooth over it. So, meshing this is not a trivial thing by any means. Okay, so even CAD software is generally very sophisticated. Or you have some complicated electrical circuit. Maybe you don't want to discretize the resistor very finely or whatever, right? So, this is a complicated step. What would be step 2? Well, step 2 is once I have read in this, once I have made this mesh file, now I start writing my code. Will I understand this? I mean, what is of interest to me in this mesh file? What am I looking for? Boundaries, not just boundaries, the locations of the triangles, the nodes of those triangles, right? That's of interest to me, because based on that, like we did in the previous slide, I can calculate the matrix. So, it looks trivial, but this is an important step. Read in the mesh file. As a computational EM engineer, you have to write this wrapper to read this mesh file in, because it will be in whatever format the CAD software did. The CAD software is a general CAD software for any problem. They may not even know or care that you are using it for computational EM. So, you have to write a wrapper that will correctly read in the data, parse the commas, whatever, all of that. So, it's fair amount of work, it is not trivial. Having done that, you have read in all of these, what do you do next? What would you do next? So, once I have read in these things, I mean, what do I read it into?
Now you make the T1, T2.
Right. Before I make the coupling coefficients, I need to create efficient data structures to store all of these elements, right. So, this is creating store the mapping, right. So, this has all of the global to local mappings, okay, list of elements to nodes, edges. You have to create all of these, right. Supposing, like in the previous example, you give a triangle. Now, once you give a triangle, you need to know which are the nodes in it. So, you need to have a way of accessing given element number, find out which nodes are there. So, you have to create that data structure, no one is going to make it for you, right. So, these 3 steps are what come under the category of pre-processing. Okay. So, now all your data is in your program. Now, we can start working with it. So, what is the next step? What we just discussed in the previous slide, that is calculating the matrix elements. So, it is called matrix assembly. Okay. So that is i.e. forming Ax is equal to b. Next obvious step, once you've got Ax is equal to b, what do? Solve it, right? What kind of complications might be here? So here is where this is in itself a separate course in numerical linear algebra. So here you have a choice. You can either do direct methods. So what are direct methods? Things which you've already seen so far: Gaussian elimination, or LU decomposition, all of those things. But you cannot keep doing this as the size of the problem becomes larger and larger. In fact, it may not even be possible to store the matrix explicitly. Then what is the alternate to direct approach are iterative methods. So typically when your problem becomes a 3-dimensional problem, doing this LU decomposition itself becomes very tedious. So you have to switch to what are called iterative methods. Any example of the most popular iterative method? Not Newton. Conjugate gradient. If you've heard the word, conjugate gradient method is a way of solving system of equations. Okay, so I mean there are families of these things. Example, various methods are there. Conjugate gradient methods. As I mentioned, this is a whole course in itself of different methods depending on the need, right? So these are this is what is called the processing. Okay. What is the next step? You have found out x. Now what? Actually calculating the quantity of interest. So in this case it will be RCS, right? So for RCS I will need some kind of a contour around the object, then I will apply Huygens principle based on the values that I have calculated of x on that and find out the quantity of interest, right. So compute if you were doing a circuit simulation, here is where you would calculate things like impedance or whatever, right, based on what you have calculated. This is okay. This is one thing. Another optional thing can be, which is very powerful, is visualizing the output. Okay, so by visualizing the output, you have got the mesh. You now visualize the values of x that you have calculated, visualize it on the mesh in 2D, 3D, whatever, right. That gives you a lot of intuition into whether your problem is has been solved correctly or not. Okay, and there are good software in the open source for doing this. So this is called post processing. Okay, so is that all? Are we done, or is there some important thing? Now imagine that you have this task you are given to calculate RCS of some object, and you come and start step 1, 2, 3, 4, 5, 6, 7, and you declare success and victory after that? No. Why? It might. How do you know it's correct or not? Well, you don't know the correct RCS. Supposing you don't have experiment. Numerical convergence is something that you have to do anyway, but it may be that you have converged numerically to the wrong answer. I mean, you have coded a consistent set of equations which are wrong. Like let's say you forgot the k0 squared term altogether. So it will give you numerical convergence, but you have solved Laplace equations from Maxwell's equation. So what would you do now? Very critical step in any computation. Right. So, what you need to do is validate your code against a known solution. Right. So, this is extremely important. Validate what kind of examples of known solutions can you think of? Okay, so basically we want what we want is a EM problem whose solution I know. So then I code up and I simulate and I should get the known answer. So what is the simplest EM problem you can think of where you know the answer analytically? Something simpler than sphere and cube. What is a problem that even a class 9 or 10 student knows the answer to? Huh? Not point source. A wave through free space. Okay, but there is no calculation involved over there. What is what? Okay, reflection coefficient. If I have a slab of glass, every school kid has done this. What is the reflection coefficient? What is the transmission coefficient? There is a formula in terms of the refractive index, and it's a how many dimensional problem? You can make it a one dimensional problem, just normal reflection and transmission. I can calculate that. If I were writing a 1D code, I know the answer. You know, reflection coefficient is n2 minus n1 by n1 plus n2. I should get the same answer back, right? So, I can now make that 2D, right? Incident at non-normal, right? So, Fresnel reflection coefficients. This can be one way of testing whether your code is giving the correct answer. Any other solutions you can think of? So, it turns out there are very few problems in electromagnetics where there is a known analytical solution, and one is this Fresnel reflection coefficients, the others are scattering from a infinite cylinder and a perfect sphere. These are called Mie series solutions. Cylinder and sphere. These have known analytical solutions. They look ugly because they are in terms of Bessel functions and Hankel functions and all of that, but you can code it and superpose your answer with this analytical answer, and that tells you that whether your code is correct or not. Short way. Then you take a leap of faith, replace that object by your object and hope everything else works. Having the luxury of validating against experimental data may not always be there. If you have it, that's great, but then you have to have confidence that your experimental configuration does not have unaccounted errors themselves. So, typically you would first validate against some known object, then use that to refine your experimental setup and back and forth. Okay. So, the real world is always very messy. So, this sort of summarizes the process flow. The FEM has a lot of coding details that are there, particularly in the pre-processing step. If you don't do it right, your code can be very inefficient in making these data structures, accessing of these data structures. Should you use object-oriented programming? All of those details, everything that you have learned, it comes into play over here. Okay. So, yeah, so that brings us to an end of the FEM. We won't go to 3D FEM, but the idea is the same, right? Shape functions, weak form, matrix assembly, calculating the quantitative interest. This is the process flow.